So we're going to talk about concentration here. So concentration is a great way of expressing how certain solutes are going to dissolve in a solution. So when we're mixing in different amounts of, it could be a liquid, it could be, generally speaking, we're talking about solids into liquids, but it could also be liquids with liquids and so on. So when we're talking about what dissolves in what, the definition here is going to be called a molarity. Molarity, by definition, is how many moles of a solute. In other words, what are you putting into the liquid divided by the liters of a solution. And generally speaking, molarity can change with temperature. So if I heat something up, I can actually dissolve more in that solution. Now, another one's called the mole fraction. We've seen this before with gases, where if you take the number of moles of A divided by the amounts, I can figure out how many moles of that I have. Also, generally speaking, it's called like the percent composition. Now, the interesting thing about these concentration values is that mole fractions do not change with temperature. So even if I increase the temperature or decrease the temperature, mole fractions are going to be the same. Molarity is a little different story. All right, let's do a quick problem here. So if you want to pause the video, go ahead and do that right now. And let me go ahead and read the problem. It says a 3.75 grams of sodium chloride is dissolved in water. The total volume of the solution is 768 milliliters. What is the molarity of that solution? So going back to this concept about dissolving and how things dissolve and like dissolves like, and things like that, we first figure out that we have grams. And what we want to do is we want to find molarity. So first step is to write down your knowns. Second step, write down your unknowns. And then from there, your formula. So the first thing is we know carefully that we need to go from grams to moles. So what we're going to do is take that 3.75 divided by the molar mass of sodium chloride, and we should get 0.0642 moles of NaCl. Now once we have that moles, we can simply divide that by that 768. So here we do is we have to convert the ml to 768 liters, and we end up getting 8.36 times 10 to the negative 2 molar NaCl. Now a couple of things I want to keep in mind is, number one, is you always want to make sure you have scientific notation, especially if you're getting numbers that are getting really large or really small. So anything less than 1, anything greater than 10. All right, second question, go ahead and pause the video if you like so you can try the video. Question is, how many ml of 0.245 molar of NaOH are needed to deliver 1.75? So again, same idea. We're just going to manipulate the equation a little bit. And so the idea here is to determine how much of the volume we have. So first off, we're going to multiply the moles times 1 liter over 0.245 moles of NaOH. And the reason why we do that is because we want to figure out, and for every 1 mole, how much, for every 1 liter, we have 0.25 moles of NaOH. So again, we're kind of using this idea, but we're kind of flipping it a little bit. Now we're going to multiply by 1,000 ml just to cancel out the liters, and we should end up with 7140 ml. Now if you want to convert it to liters, you can, but generally speaking, it's asking here for an ml. So the answer is 7140 ml of 0.245 molar, and it's going to deliver 1.75 of moles. All right, so let's move on to something a little different here. So let's assume we're preparing 100 ml of 1M using 1.25 millimeters of NH3 distilled water and 100 ml in a graduated cylinder. How would you do this? Okay, so these are very classic examples of more of an experimental part of diluting things. So if I ask you, I want to prepare 100 ml of 1 molar using 1.25, and you have a 100 ml cylinder, let's go ahead and run it. So the first step is you want to find the number of moles of NH3 required. So it's a very classic example of using molarity to backtrack. So we're going to use the 0.1 solution multiplied by 1 mole, which gives us a molarity, and that should give us 0.1 mole of this amount. Now again, this 1,000 ml that you're getting right here has 0.1 molar is based off of this idea of that 100. So we need 0.1 mole of that NH3. All right, step 2, we're going to find the volume of the 1.25 mole required. So what we're going to do is multiply that by the 1.25 moles that is giving us in this case. Multiply by 1,000 and it should give us 80 ml. So now, in order to do the actual calculation, we're going to pour 80 ml of the 1.25 molar into a graduated cylinder, and then we're going to add distilled water until you have 100 ml of the solution. So in other words, we're going to add about 20 ml of that distilled water to make that 100. Okay. All right, so let's talk a little bit about mole fractions here, and going back to the same idea of percent comp and what that mole fraction looks like. So here is our mole fraction of XKOH and XH2O in a solution that's prepared by dissolving 1.5 moles of KOH in 1 gram of H2O. So the first question is find the moles of H2O. So what we're going to do is we're going to multiply that by 1,000 divided by 1 kilogram, and that's going to give us your kilogram amount in grams, and obviously we multiply that by our molar mass, and what that's going to give us is 56 moles of H2O. So very classic example of going from a gram to a mole, and that's going to give us our N value. Second thing is we're going to calculate the mole fraction. So what we need to do is figure out what the NKOH is and what the NH2O is. So what we're going to do there is take the 1.5 moles divided by 1.5 moles plus 56, and we're going to get the 0.026 for that. And once you do that, you're going to get 1 minus 0.026, and that's going to equal 0.974. So just to recap real quick on the mole fractions, I mean, once you take that, you're going to subtract it by the 1, because once they both add up, you're going to end up getting that 0.974. All right. Okay, well, that ends our mole fraction portion and our calculations for concentrations.